Usually when you prep for a test or when you dive into a new technical subject, there's this expectation of like precision.
Oh, yeah, absolutely. You expect clear boundaries.
Right. You take a practice quiz, and it acts almost like a medical x-ray. It shows you this bright, jagged white line of exactly what you need to know.
Yeah, the professor just points to the screen and says, there's the fracture. Learn the specific formula to fix it.
Exactly. And it's comforting, right? I mean, we love it when knowledge is visible, when it's neatly categorized into those little multiple choice boxes.
No, it feels binary. It's clean. Something is either on the test or it's not.
Right. But then you take that multiple choice mindset and you step into the actual sprawling theoretical landscape of advanced machine learning.
Oh, boy. Yeah.
Specifically, I mean, the deep end of reinforcement learning and game theory. And suddenly that pristine X-ray machine just completely shatters.
It really does. You aren't looking at a clean diagnostic anymore at that point.
No, you are wading into some seriously muddy waters.
And, that murky territory is actually where the real engineering happens. I mean, the practice modules give you this illusion of mastery because they mostly just test definitions.
Right, just vocabulary, basically.
Exactly. But the raw lecture transcripts, the actual uncut conversations the professors are having with the students, those reveal massive hidden depths.
Yeah, the math behind those definitions.
Yeah.
The scenarios where the definitions completely break down in the real world.
Which is exactly why we're here today doing this.
Yes.
Yeah.
We are taking the ultimate deep dive for you today. We got our hands on a stack of machine learning practice quizzes, the ones covering Markov decision processes, reinforcement learning, and game theory.
But we didn't just read the answer key.
No, instead of doing that, we cross-reference those exact quizzes directly against the raw lecture transcripts. And wow, what we found was a massive gap.
A truly staggering gap, really. I mean, entire algorithms, deep philosophical debates, and strict mathematical constraints were taught in agonizing detail in the lectures. But then they were mysteriously just completely absent from the practice quizzes.
It's wild.
Yeah.
So today, we are going to bridge that gap. We are going to take the concepts you think you know from the quizzes, and we are going to completely invert them.
We're going to push them to their absolute breaking point.
Right. Dig into the hidden edge cases and run through real-world engineering scenarios where a multiple-choice guess could, crash $1 million system.
Yeah, you should consider this a stress test for your brain.
Exactly. And we are going to trace the logic using absolutely nothing but the provided source material.
Right. No outside assumptions whatsoever, just pure logical deduction straight from the lectures.
So let's jump right into the deep end. The quizzes establish a very clean baseline for Markov decision processes, or MDPs.
Yeah, the foundational stuff.
Right. They test the basic knowledge that an NDP models decision-making with uncertainties, and that you calculate how good a situation is by just summing up your rewards. Very straightforward.
Yeah, but they assume a stationary policy.
Right, stationarity. Break that down real quick.
Well, stationarity is the absolute bedrock of how we usually solve MDPs. It assumes that the physics of your environment, the rules of the game, and, most importantly, your optimal policy, they all remain perfectly identical regardless of what time step you are currently in.
So, if the best move is to go left on Tuesday, the best move is to go left on Friday.
Exactly. The rules don't change just because the clock ticked, but here is the massive caveat that the quizzes completely skip over.
Lay it on me.
Stationarity absolutely relies on having an infinite time horizon.
Wait, infinite. So the game essentially has to go on forever.
Yes. For the math to be that clean, you have to assume there is no end of the world coming.
Okay, let's play with that because that's fascinating. What happens if we introduce a finite time horizon? Because, in the real world, batteries die. Stock markets close at 4 p.m.
Exactly.
How does a finite clock fundamentally break that stationary assumption?
Oh, it completely destroys it. Time suddenly becomes this critical dimension of your state. So the professor in the transcript uses this great grid world example.
Okay, like a little maze.
Right. Imagine you are navigating a grid to reach a goal, but there's a dangerous trap nearby. Now, in an infinite horizon, your optimal policy might be to take a very long, very safe route around the absolute edge of the board to avoid the trap.
Because you have all the time in the world, there is no rush.
Exactly, no rush at all. But what if I am standing on that exact same square looking at the exact same trap, but my internal clock says I only have 3 steps left before the game ends?
Oh, wow. Instead of 3 million steps.
Right. Then your entire policy flips on its head. You no longer have the luxury of taking the long, safe route. You are mathematically forced to take the risky, short route right past the trap.
Because it is literally the only physical way to reach the positive reward before your time runs out.
Precisely. So, look at what just happened. You are in the exact same physical state on the exact same square.
But my optimal action is completely different.
Yes. The policy becomes completely dependent on the time remaining. You lose the stationarity of your policies.
Wow, that's wild.
Yeah.
And mathematically, what does that mean for the system?
Well, mathematically, it means instead of solving for one universal set of rules for the whole board, you have to solve for a completely different set of rules for every single tick of the clock.
Oh man, that sounds exhausting.
It makes the math incredibly heavy, almost computationally impossible for complex environments.
Which brings up this wild paradox I noticed in the transcripts. Assuming infinite time makes the math easier because the rules stay the same, right?
Yes, exactly.
But assuming infinite time also creates a massive mathematical nightmare when it comes to actually adding up the rewards over time. I call this the living forever critique.
Ah, yes, the existential dilemma of living forever. The transcript spends quite a bit of time on this exact issue.
Right, because if you are an immortal AI agent and you are just adding up rewards forever, your total score is going to be infinity.
Yeah, there's no cap.
So let's do a thought experiment here. Imagine two immortal AI agents. Agent A receives a steady reward of +1 every single day, forever.
Okay, a nice stable life.
Right. But Agent B receives a +1 every day, but also occasionally hits a jackpot and gets a +2.
Oh, nice.
So just intuitively, Agent B obviously has a better life, right? More reward is better than less reward.
Intuitively, human logic definitely says yes. I mean, you would never regret being Agent B because you are objectively experiencing more good things.
Right.
But mathematically, under a strict, simple addition scheme, we hit a brick wall here. Infinity equals infinity.
Wait, really? Even though Agent B is clearly adding those +2s into the mix.
Yes, think about it. If Agent A accumulates +1 forever, their total mathematical utility is infinity. If Agent B accumulates +1 and occasional +2s forever, their total utility is also infinity. They are mathematically indistinguishable.
So if an AI has to evaluate and choose between path A and path B, and it sees that both paths evaluate to infinity, it just throws its hands up.
Exactly. The choice becomes meaningless. The math completely fails to guide the agent toward the intuitively better path.
That is wild.
And this is exactly why the lectures introduce the discount factor, which is denoted by the Greek letter gamma.
Right, gamma. Now, I noticed the quizzes do test the basic definition of gamma, that it makes the infinite sum finite, but they don't really test the why.
No, they just treat it like a magic trick.
Yeah, so gamma is basically a dial between 0 and 1.
Right.
And we multiply our future rewards by it.
Right. And because it's a number less than 1, say it's 0.9, rewards further in the future get multiplied by 0.9, and then the next step is 0.81, then 1.72, they shrink.
Okay, there was a fascinating tangent in the transcript where the professor explained this shrinking effect by comparing it to the singularity.
Yes, the technological singularity. It's the concept of a computer designing a faster computer in half the time, which then designs another computer in half that time.
Okay, so generation 1 takes a year, generation 2 takes 6 months, generation 3 takes 3 months.
Exactly. And because that sequence of fractions, a half, a quarter, and 8, because it mathematically sums to a finite number, you can theoretically have an infinite number of computer generations within a finite amount of human time.
Wow.
It is what we call a geometric series.
And gamma acts exactly like that geometric series for our AI's rewards.
You got it. A discount factor mathematically forces an infinite sequence of future rewards to act like that geometric series. It results in a bounded finite value.
It puts a ceiling on it.
Specifically, it caps at the maximum possible reward divided by 1 minus gamma. So it mathematically caps infinity, which finally allows the AI to actually compare the values of two infinite paths.
Because suddenly path A is worth 100 and path B is worth 150 instead of both being infinity.
Exactly. Without gamma, the whole reward system collapses.
That is so cool. And this mathematical trick of keeping preferences stable over time leads to another edge case I pulled from the transcripts.
Oh, let's hear it.
So the quizzes test the formula for calculating utility, but they don't ask why we strictly use addition to combine these discounted rewards. I mean, why not multiply them or average them?
Oh, that is a great question. That comes down to a strict requirement called stationary preferences.
Stationary preferences.
Yeah. If an AI decides that a certain sequence of states is better than another sequence today, that preference logically must hold true tomorrow.
Okay, that makes sense.
So if you multiplied rewards, a single zero reward anywhere in the future would instantly wipe out all previous gains. The whole path becomes zero.
Oh, right, because anything times 0 is 0.
Exactly. Or if you average them, a long streak of mediocre rewards would massively dilute a huge early jackpot. Your preferences would constantly flip-flop based on the math operation, not the actual environment.
So addition is literally the only mathematical operation that ensures if path A is better than path B right now, it will mathematically remain better no matter how the sorting states shift over time.
Exactly. It's not just an arbitrary choice by some programmer. It's a structural requirement for the AI to maintain a consistent personality, so to speak.
I absolutely love that. Okay, let's pivot slightly to how these agents actually learn these paths. The quizzes spend a ton of time on Q learning.
Oh, yeah, the classic.
Right, they ask basic things like what a policy is, which is just a map of states to actions. But Q learning is famously model-free,
Right.
meaning the AI wakes up with absolutely no knowledge of the environment.
It doesn't know the transition function, which is the physics of the world,
Mhm.
and it doesn't know the reward function, which is the rules of the game.
So here is the missing conceptual question that the quizzes ignored. If it doesn't know the physics and it doesn't know the rules, how on earth does it actually build a policy? It's like navigating a dark maze without a blueprint.
It is exactly like that. You were just wandering around in the dark, literally bumping into walls. Q-learning solves this through something called temporal credit assignment.
Temporal credit assignment.
Right, using a very specific update equation.
Hmm.
So the agent just observes raw data from its wandering. It observes. You start in a state, you take an action, you land in a next state, and you get a reward.
Okay, SAS prime R.
Exactly. The AI takes the immediate reward it just bumped into and adds it to the discounted expected value of the next state it landed in.
Oh, so it's looking ahead.
Right. It effectively backs up the value from the future state to the current state action pair. It leaves this little mathematical scent trail of value behind it as it wanders.
That's a great visual.
Yeah.
But wait, a Q value is just a number, right? It's a score for taking a specific action in a specific state.
Yes, just a number.
But that's not a policy. A policy is a rule book that says, when in this state, do this action. How do we get from a heat map of random scores to an actual policy?
You extract it indirectly using the argmax operator.
Argmax. Bring that down for me, because that sounds intimidating.
It's actually really simple. Argmax just means the argument that produces the maximum value. So if you are standing in a state, you don't need a rulebook to tell you what to do. You just look at the 4 possible actions you can take, say, up, down, left, right. You check their Q values that you've been updating, and you simply pick the one with the highest number.
I see. So if up has a score of 10 and down has a score of 2, argmax just automatically grabs up.
Right. You don't need a pre-written rulebook if you have a perfect heat map of values around you.
That is so elegant. You know, the history of how we got here is actually fascinating, too. The transcript mentions that computer scientists actually stole the term reinforcement learning from psychologists.
Oh, yeah. From psychologists who were studying animals, like rats in a maze trying to find cheese.
Right. But the professor points out that they fundamentally altered the goal when they digitized it.
They really did. See, the psychological model was entirely focused on strengthening connections. A rat hits a lever, gets some cheese, and the physical neural connection between lever and cheese gets stronger in its brain.
So it's just a habit forming.
Exactly, habituation. But when computer scientists adopted the framework for AI, they shifted the focus entirely to maximizing rewards.
Wait, how's that different?
Well, an AI isn't just forming a blind habit. It is mathematically calculating the optimal sequence of actions over time to extract the absolute maximum possible value from the universe.
Oh, wow.
It's a subtle semantic shift, but it's a profound philosophical difference in what learning actually means to a machine versus a rat.
Which perfectly explains why we sometimes run into scenarios where the machine learns the exact wrong lesson.
Oh, constantly.
Let's run our first engineering scenario based on the transcripts.
Yeah.
Imagine you are building a Q-learning agent, but it gets stuck.
Okay.
Let's say because of some weird quirk in how the program booted up, a terrible, highly suboptimal action suddenly got a massive, artificially inflated Q value.
Like a false positive.
Right. So your agent tries it, gets a little tiny reward, and just keeps picking it, completely reinforcing its own bias and totally ignoring vastly superior options that are right next door. How do you break an AI out of that loop?
Well, the transcript specifically warns against just completely randomizing everything to start over because random restarts take far too long computationally.
So you can't just unplug it and plug it back in.
No, you have to be smarter. To fix that initialization bias, you deploy a specific strategy called epsilon greedy exploration.
Okay, epsilon being another Greek letter we use as a dial.
Yes, exactly. Epsilon represents the probability that the agent will ignore its current knowledge, ignore the argmax, and just do something completely random.
How interesting. So if epsilon is set to 0.1, 10% of the time, the agent will randomly throw a dart instead of taking the safe, greedy action.
You got it. It forces the AI to occasionally take a downhill step, exploring a really bad-looking option that might actually lead to a hidden jackpot just around the corner.
That makes a ton of sense.
It's heavily related to a physics concept called simulated annealing.
Like with metals.
Right. You start with a very high epsilon, lots of randomness, which is like heating up metals so the atoms jump around wildly. Then, over time, you steadily decay epsilon. You slowly cool the metal down. As the agent builds an accurate map of the maze, it explores less and exploits its knowledge more, eventually locking solidly into the true optimal path.
I love how physical these concepts get when you really unpack the analogies. But, let's look at the actual math under the hood of these solutions.
Let's do it.
Because the quizzes asked very basic questions about solving MDPs, but they completely ignored the Bellman equation.
Oh, man.
And the professor literally calls the Bellman equation the most important equation ever.
It really is the engine of all of this.
Right. And specifically, the quizzes ignore why it is so mathematically frustrating to deal with. Why does solving an MDP involve nonlinear equations?
It's all because of that max operator we were just talking about with the argmax.
Okay, how so?
Well, when you want to solve an environment with, say, exactly 100 states, you end up with 100 equations and 100 unknowns.
And, my college linear algebra professor would tell me, great, just put it in a matrix, invert it, solve it. Easy day.
Right. Linear algebra is beautiful and clean like that. But the Bellman equation asks you to find the value of a state by looking at all future actions and taking the maximum one.
The max operator.
Yes. The max operator creates a piecewise function. It introduces a sharp, jagged corner into the math. You can't draw a smooth curve through it. As soon as you throw a max operator into a clean system of equations, it shatters the linearity.
Oh, I see. You can't just invert a matrix anymore.
Not at all, because the numbers keep shifting dynamically depending on which action is currently evaluating as the maximum.
It's like trying to solve a Sudoku puzzle where the numbers physically morph every time you look at them.
That is a terrifying but very accurate analogy. So an algorithm like value iteration just has to brute force it.
It just grinds through it.
Right. It starts with a bunch of totally wrong, arbitrary numbers and repeatedly pushes them through that nonlinear Bellman equation until they slowly, agonizingly converge on the truth.
But the transcript introduces a second method, right? Policy iteration.
Yeah.
And the professor says policy iteration structurally bypasses this nonlinearity entirely. How does it do that?
It pulls a brilliantly simple mathematical trick. Policy iteration starts by locking in a specific fixed policy.
A fixed policy.
It tells the agent, for right now, just assume we are definitely 100% taking this exact action in this exact state.
Wait, I think I get this. If you force the agent to take a specific action, you remove the choice.
Yes, you got it. By fixing the policy, you completely remove the max operator from the equation. You are no longer asking what is the maximum of all these choices. You are just asking what is the mathematical value of this one specific choice.
Oh, that's like using a GPS.
How so?
Well, if I try to calculate every single possible route to my destination simultaneously, my phone will probably crash. That's the nonlinear nightmare. But if I just lock in the decision to take the highway, even if it's a suboptimal guess right now, suddenly calculating the exact arrival time for that specific route becomes really simple math.
That is a phenomenal analogy. Yes, exactly. Once the max choice is removed, that terrifying nonlinear system instantly converts into a set of highly friendly, easily solvable linear equations.
Amazing.
Policy iteration solves those linear equations to find the exact value of your current GPS route. Then it steps back, looks at the new values, and asks, okay, based on this math, can we improve this route?
So it toggles back and forth.
Right. It toggles between linear evaluation and a discrete improvement step, completely sidestepping the nonlinear nightmare.
And here's a subtle edge case about value iteration that I pulled from the transcripts.
Yeah.
When we brute force those utilities, do we actually need absolute perfect mathematical convergence to be successful.
Oh no, not at all. And this is a crucial engineering reality. The goal of value iteration is not perfectly calculating utilities out to the 100th decimal place.
Okay, so what is the goal?
The goal is simply extracting the correct optimal policy.
Oh, so once the utilities are distinct enough that the argmax clearly points to the correct action, we can just stop doing the math.
Exactly. If action A is evaluating at 10.1 and action B is 9.9, you know A is better. You don't need to waste expensive computing power calculating them out to 10.145 and 9.876. The policy has already converged, even if the utilities technically haven't.
That makes total sense practically. Okay, let's talk about the learning rate, because this was another massive blind spot in the quizzes.
Oh, the learning rate is fascinating.
When an agent is updating its values, it uses a learning rate denoted as alpha. It determines how much new information overwrites old information. The quizzes test what it is, but completely ignore the strict mathematical constraints required for it to actually work.
Yeah, and this is one of the most elegant concepts in the entire course, honestly. For a Q-learning algorithm to successfully converge on the absolute truth, the learning rate has to shrink over time. But it has to shrink in a very specific, paradoxical way.
Right, the professor introduces two strict conditions. The first is that if you sum up all the learning rates to infinity, the total sum must also equal infinity.
Right. And the professor suggests using the sequence where alpha equals 1 over t, where t is the time step.
So at step 1, the learning rate is 1 over 1, then 1 over 2, 1 over 3, 1 over 4.
Yes. And if you add that harmonic sequence together infinitely, the sum literally goes to infinity. It acts like a natural logarithm.
Why is that vital?
This is vital because it ensures the agent retains an infinite amount of learning power. No matter how badly the agent initialized its early guesses, an infinite sum guarantees it can always travel as far mathematically as it needs to reach the true value.
Oh, I see. So it basically never runs out of gas.
Exactly.
Okay, but what's the second condition?
The second condition is where the paradox comes in. The sum of the squares of those exact same learning rates must be strictly less than infinity. It must be a finite number.
Okay, wait, let's unpack this carefully.
Yeah.
And I take that same sequence, 1, 12, 13, 14, and I square each term.
Yep.
I get 1, 14, 19, 1, 16. You're saying if I add that sequence up to infinity, it doesn't go to infinity. It stops at a real number.
It shockingly converges to a finite value. The transcript explicitly notes this is the famous Basel problem in mathematics. That infinite series of squares converges precisely to pi squared over 6.
Pi squared over 6. Pi shows up in a reinforcement learning algorithm about grid worlds.
It is incredible, isn't it? Math is all connected, but conceptually, the fact that the sum of squares is finite means that the sizes of the actual updates strictly shrink to 0 over time.
Oh, I think I get it. The infinite sum ensures it has the gas to travel the distance, but the finite sum of squares ensures that once it gets there, it settles down.
Exactly. It ensures that as time goes on, the agent stops violently overreacting to every new piece of random noise it bumps into. It allows the algorithm to settle exactly on the expected value, the true mean, rather than just bouncing around forever.
Wow. And this mathematical settling relies on probabilities overlapping in really interesting ways. Let me throw an edge case at you from the grid world example.
Bring it on.
So, the professor describes a noisy world where an action has an 80% chance of doing what you actually want, a 10% chance of veering right, and a 10% chance of veering left.
Okay, a slippery grid.
Right. If your optimal path is exactly 5 steps long, what is the probability of succeeding if your first 4 actions go completely wrong, but your final action goes right?
Well, it sounds like a trick question, but it actually gets to the very heart of stochastic environments.
How so?
If you need to go right and you accidentally veer up, but then on the very next turn, you try to go up and you accidentally veer,
Right.
you end up in the exact same physical spot as if everything went perfectly.
Oh, the errors just cancel each other out.
Exactly. The raw probability of 4 specific errors and 1 success occurring in that exact order is tiny, obviously, but mathematically, you have to factor all those microscopic probabilities in.
Right.
When you sum them all up, the overall probability of success remains identical regardless of which specific 5-step optimal path you choose.
It's just the law of large numbers smoothing out the chaos over time.
Perfectly so.
Okay, let's step out of single-agent environments for a minute and cross the bridge into game theory.
Oh, now it gets fun. We're no longer alone.
Right. We have opponents now.
Yeah.
The quizzes cover the iterated prisoner's dilemma, where 2 players can either cooperate or defect.
The classic setup.
And the quiz confirms that if you know exactly when the game ends, the rational mathematical choice is to always defect.
Right, through a process called backwards induction.
Explain that real quick.
If I know for a fact the game ends on round 10, I'm going to defect on round 10 to protect myself and grab the cash. But since you know I'm going to defect on 10, your best move is to defect on 9.
And then I know you'll defect on 9, so I defect on 8.
Exactly, and it unschools all the way back to round 1. Everyone just defects immediately.
Right. But the lectures take this way further. What if the end is uncertain? Here, we bring back our old friend, gamma.
Ah, gamma returns.
But gamma isn't just a discount factor anymore, right? It represents the actual probability that the game continues to a new round.
Exactly. It's the chance of survival.
So the inverse question here is, apply this uncertain ending to determine the exact mathematical tipping point, where cooperating against the famous tit-for-tat strategy actually becomes better than just blindly defecting.
This is a beautiful intersection of reinforcement learning and game theory right here. So you're facing tit for tat. This opponent cooperates on round 1 and then simply mimics whatever you did on the previous round forever.
A pure copycat.
Right. Your optimal response depends entirely on gamma.
Because gamma tells us how long we expect to interact with this copycat.
Precisely. The expected number of rounds is mathematically 1 divided by 1 minus gamma. If gamma is extremely low, say 0.05, the game is probably ending almost immediately.
And the transcript breaks down the specific mathematical tipping point, right? Gamma equals 16.
Yes, that's the magic number. If gamma is less than 16, the probability of the game ending quickly is so incredibly high that there is literally no mathematical value in building a long-term coalition.
You just defect, take the quick cash, and run.
Exactly. But if gamma is greater than 16, say gamma is 0.9.
Then the expected number of rounds stretches way out.
Yes, and the math flips completely. The long-term accumulated payoff of mutual cooperation fundamentally dwarfs the short-term one-time gain of a single defection.
Wow.
The math literally changes your optimal behavior from selfish paranoia to collaborative diplomacy, strictly based on the probability of a future existing.
That is deeply philosophical for a math equation. But, game theory is obsessed with worst-case scenarios.
Yeah.
And this brings us to a massive concept that the quizzes totally ignored: implausible threats and subgame perfection.
Oh, this is crucial.
Let's look at that tit-for-tat strategy again. On paper, it seems perfectly fair. You cooperate, I cooperate, you defect, I punish you by defecting. It's beautifully
It
balanced.
seems like it, yeah.
But the professor explicitly states tit-for-tat is not subgame perfect. Why not?
Because of what happens when a mistake occurs. See, a strategy is only subgame perfect if the threats it makes are actually plausible for a rational agent to carry out.
Plausible to carry out. What do you mean?
Well, what if we are in a noisy environment? Say we've been cooperating peacefully for 100 rounds, but an actuator slips on your machine and you accidentally defect.
Oh, man. So I didn't mean to defect, but the system registered it as a defection.
Right. How does tit-for-tat respond to that?
Well, it rigidly mimics my last move.
Mhm.
So on the next turn, tit-for-tat punishes me by defecting.
Exactly. But by the very next term, you've already realized your physical mistake and you've gone back to cooperating.
Right, so I cooperate, while tit-for-tat defects against me.
Yes, and now you feel wronged. You cooperated and the machine just defected against you. So on the next turn, you defect in retaliation.
But by then, tit-for-tat has seen my cooperation from the previous turn, so it cooperates.
Exactly. You are perfectly out of sync. Defect, cooperate. Cooperate, defect.
Oh, it triggers an endless, catastrophic loop of alternating retaliation.
Yes. Because of one tiny slip, you destroy each other's scores forever. A perfectly rational agent wouldn't follow through on that threat because it essentially leads to mutually assured destruction. It cannot computationally recover from a simple error. Therefore, it is mathematically not subgame perfect.
Okay, so let's run our third engineering scenario then. You are running an iterated prisoner's dilemma simulation over thousands of rounds, and you know your environment is noisy. There will absolutely be accidental slips.
Guaranteed.
How do you prevent that endless cycle of vengeance?
You deploy a strategy called Pavlov.
Pavlov. The transcript describes Pavlov's rules, right?
Yeah.
If we both cooperated last turn, I cooperate. If we both defected, I defect. But if you defected and I cooperated, I punish you by defecting. But then I return to cooperation on the next turn regardless.
Right, regardless of what you do.
Wait, if an opponent just backstabbed me and I punish them once, but then immediately offer an olive branch the next turn,
Yeah.
doesn't that just make me a complete sucker?
In the short term, maybe you get taken advantage of once or twice. But mathematically, in the long term, it is genius. It is the definition of subgame perfect.
Walk me through it. Let's trace that noisy slip again.
Okay. You accidentally defect. Pavlov punishes you by defecting on the next turn. But instead of getting locked into that permanent death spiral we just talked about, Pavlov has a built-in reset button.
Ah.
After that single punishment, Pavlov automatically offers a cooperative move.
Like forgiveness in a relationship. We fight, we make our point, but then we actively choose to reset the baseline to cooperation.
That's a great way to look at it. Exactly. The transcripts map out the state sequences, and a Pavlov machine will always end up returning to mutual cooperation from any state, regardless of noisy slips or even malicious starts by the opponent.
So it's fundamentally stable.
Yes. It can make a threat, execute the punishment, and know that carrying it out won't cost it long-term ruin.
And when we talk about rigid strategies versus adaptable ones, there's a very subtle edge case the professor mentions, the analogy of chocolate and bacon.
Oh, I loved that part. Yes, the professor uses chocolate and bacon to describe pure strategy.
Pure strategy.
Yes. A pure strategy in game theory means a deterministic mapping, a 100% rigid commitment to a single choice in a given state. You're either all in on chocolate or all in on bacon.
There is no mixing, no probability distribution.
Right. No 60% chocolate, 40% bacon choices.
Which leads right into another edge case about terminology that I find really interesting. In these games, you have to guarantee yourself a baseline of success, even if the opponent plays perfectly against you.
Your safety net, essentially.
Right. The quizzes use the term min-max profile, but the professor in the transcript aggressively prefers the term security level profile. Why make that semantic distinction? Does it matter?
It matters deeply because language matters mathematically. The term min-max is historically associated with those rigid, pure strategies, the chocolate and bacon we just talked about.
Okay.
But think about it. If you were playing rock, paper, scissors against a psychic, a pure strategy guarantees you lose.
Right. If my pure strategy is to always play rock, I always lose.
Exactly. So the term security level profile inherently acknowledges the mathematical necessity of mixed strategies.
Meaning I have to be unpredictable.
Yes. It implies that to truly secure your baseline against a perfect opponent, you might need to act probabilistically playing rock 33% of the time, paper 33%, scissors 33%.
That concept actually feeds directly into a piece of mathematical folklore mentioned in the transcript. The folk theorem.
Oh, the folk theorem, yeah.
What is the difference between a folk theorem in general math and the formalized folk theorem in game theory?
Well, in general mathematics, a lowercase folk theorem just means an unpublished result passed through oral tradition. It's basically something every mathematician knows is true, but no one ever bothered to formally publish a rigorous paper on it.
It's like an urban legend with a mathematical proof?
Basically, yeah. But in game theory, uppercase folk theorem is a specific, formalized, proper noun.
What does it mean?
It mathematically describes the exact set of feasible payoffs in a repeated game that are strictly better than your security level profile.
So it's the good zone.
Right. It formally defines the entire universe of acceptable outcomes where both players do better than their worst-case baseline.
Let's talk about those worst-case baselines and hidden information.
Yeah.
Because this is where game theory gets incredibly human.
It really does.
The transcripts break down a hidden information game called mini poker, and it's brilliant. Let me outline the rules for you.
Go for it.
Player A is dealt a single card from a deck of half red, half black cards. Only player A sees the card. Player A can either hold or resign.
Okay.
If player A resigns, they lose 10 cents to player B immediately. If player A holds, the turn passes to player B, who still hasn't seen the card, and player B has to choose resign or C.
Right. And the payouts change based on B's choice.
Exactly. If player B resigns, they pay player A 10 cents. If player B says, I want to see the card, the bet goes up. If the card was red, player A loses 20 cents, but if the card was black, player A wins 30 cents.
Got it. It's a great little simplified model.
Okay, here's the edge case question from this. Why is there mathematically 0 point for player A to ever resign if they draw a black card? I mean, maybe they want to throw player B off their scent. Play some deep mind games.
This is where we have to trace the actual decision tree from the transcript. Remember, game theory assumes rational actors optimizing for payouts.
Right, no emotions allowed.
Exactly. If player A draws a black card and resigns, the payout is exactly 0 relative to their baseline. They just fold and take the loss.
Okay.
But look at the branches. If player A decides to hold that black card, the decision passes to player B.
Right.
If player B gets scared and resigns, player A wins 10 cents.
Okay.
If player B gets bold and demands to see the card, player A flips the black card over and wins 30 cents.
Oh, I see what you're saying.
Yes. Both possible outcomes of holding a black card are positive for player A, plus 10 or plus 30. Therefore, holding is a strictly dominant strategy. Resigning yields 0.
So there is literally no mathematical universe, no complex psychological mind game where trading a guaranteed positive return for 0 makes sense.
Exactly. That branch of the decision tree where they resign with a black card can simply be pruned and completely ignored by the algorithm.
You know, it's fascinating how mini poker is just a tiny, tiny example of a much larger architectural framework that the professor introduces. This brings us to a massive missing area from the quizzes. Stochastic games.
Also called Markov games, yes.
Right.
They were actually introduced by Lloyd Shapley before Richard Bellman even formalized MDPs. It is sort of the grand unified theory of all this. It has multiple states, multiple players, transition matrices, and complex reward functions all interacting.
But the professor does this beautiful thing in the lecture where they show how you can apply very specific constraints to this giant, complex stochastic game and collapse it down into 3 completely different models that we've already discussed. How does that work?
It's all about zeroing out variables. It's really elegant. Let's look at the first constraint. What if you constrain the environment so that player 1's reward is exactly the inverse of player 2's? Mathematically, R1 equals negative R2.
So whenever I win, you lose.
Exactly. Under that constraint, the grand, complex stochastic game instantly collapses into a classic zero-sum game. The sum of the rewards is always perfectly 0.
And the transcript mentions a strict limitation about zero-sum games, right? A sort of edge case. They only work for exactly 2 players. Why is that?
Because if you introduce a third player, they act as a mathematical disruption to the strict opposition.
How so?
If player 1 wins 10 and player 2 loses 5, player 3 has to lose 5 just to keep the sum at 0. The third player essentially messes with the numbers and forces the players to start considering mutual alliances to offload the losses onto the third guy.
Oh, I see.
Functionally, introducing a third player breaks the strict opposition and turns the whole dynamic into a general sum game.
That makes perfect sense. Okay, what's the second way to collapse a stochastic game?
Well, what if we apply a constraint where player 2's actions have absolutely 0 impact on the transition probabilities, and player 2's rewards are just a constant 0 forever?
Then player 2 is effectively a ghost. They can press all the buttons they want on their controller, but nothing happens in the game.
Right. Player 1 is the only agent actually affecting the physical world. Under this specific constraint, the multi-agent stochastic game collapses entirely into a single-agent Markov decision process.
So an MDP is literally just a multiplayer game where the other player's controllers are unplugged.
That is a perfect way to phrase it, yes.
And the third constraint,
What if you restrict the environment to exactly one state?
if there's only one state, we can't transition anywhere. The whole transition matrix is useless.
Exactly. You just stay in that single room playing the exact same scenario over and over again. The physical state never changes, only your actions and your rewards do. The stochastic game collapses into a repeated game.
Like the iterated prisoner's dilemma.
Precisely. 3 completely different conceptual frameworks, all revealed to be the exact same underlying math equation, just with different variables zeroed out.
Mind-blowing. Okay, since we are firmly in the realm of multiplayer environments now, let's run another engineering scenario. Scenario 2.
Let's hear it.
You are designing a cybersecurity algorithm. You know for a fact you're playing against a perfectly rational, highly malicious human hacker whose only goal is to maximize your system downtime.
A true adversary.
Right. You don't care about trapping them or catching them. Your only goal is to guarantee a baseline of defense regardless of what complex attacks they throw at you. What game-theoretic algorithm do you deploy?
You deploy the Minimax algorithm, also known as Maximin,
Why Minimax specifically?
because this is a true 2-player zero-sum game. The hacker's gain is exactly your loss. Minimax operates on the core assumption that the opponent will always take the action that minimizes your reward.
They will always do the worst possible thing to you.
Right. And because the hacker is perfectly malicious, assuming the absolute worst-case counter strategy is completely mathematically sound here, Minimax calculates the highest possible minimum outcome you can secure.
Meaning it guarantees your security level profile against an optimal attack.
Exactly. You lock in your safety net.
But Minimax has a fatal flaw if the environment changes, doesn't it? This leads to our final missing conceptual area: general sum games and computational limits.
Oh, this is where algorithms really hit a wall.
Right. The quizzes heavily praise Q-learning and Minimax, but what happens when you combine them into an algorithm called Minimax Q, and then you try to deploy it in a general sum game?
It fails miserably.
Why does it fail?
Because in a general sum game, R1 does not strictly equal negative R2. The sum isn't zero. Mutual benefit is actually possible. We aren't strictly enemies, we might be frenemies.
So if mutual benefit is possible, Minimax Q's core assumption that the opponent spends every waking second trying to destroy you is mathematically incorrect.
Right. And what happens when you operate on that incorrect assumption? It leads to incredibly paranoid, overly pessimistic, highly suboptimal policies.
You're just constantly defending against nothing.
Yes. You leave money on the table because you are too busy defending against attacks that aren't actually coming. So researchers tried to fix this specific issue by creating Nash Q.
Nash, as in John Nash,
Yeah.
calculating the Nash equilibrium.
Exactly. Instead of minimizing a maximum loss, Nash Q tries to compute the true Nash equilibrium at every single step to find the actual value of the game for both players.
That sounds like a brilliant fix. Does it work?
Conceptually, yes, it's beautiful. Computationally, it is a total disaster, especially when you pair it with value iteration.
Why is it a disaster?
Two massive problems emerge. First, in a general sum game, there isn't always a unique solution. There can be multiple Nash equilibria with completely different values.
Oh, so the algorithm's value iteration literally doesn't know which value to converge on.
Right, it's trying to hit a target that suddenly splits into three completely different targets.
That sounds problematic.
It is, but the second problem is the real killer: pure computational load. Computing a Nash equilibrium is notoriously difficult. The transcript notes it is in a mathematical complexity class called PPA time.
Explain PPD hard for me. We hear NP hard all the time in computer science, meaning it takes exponential time to solve as the problem grows. What is PPA?
Okay, imagine trying to find the exact center of a massive, complex maze, but every time you take a step, the walls dynamically shift based on your movement.
That sounds impossible.
Well, a mathematician can prove to you on paper that a center must logically exist, but actually writing a computer algorithm to physically trace the path to find it is intractably complex.
I see.
PPA hard problems are ones where a solution is guaranteed to exist like a Nash equilibrium, but finding it takes a mathematically unreasonable amount of time.
So attempting to compute a PPAD hard problem at every single iterative step of a learning algorithm
Is practically impossible. The heat death of the universe would occur before your laptop finished computing a complex Nash Q general sum game.
which leads perfectly into our final engineering scenario. Scenario 5.
Okay, let's tie it together.
You are designing that exact general sum multi-agent game. Your agents need to cooperate in this environment. But, as we just firmly established, computing Nash Q is computationally impossible. PPAD hard.
Right.
However, your agents are allowed to broadcast non-binding intentions to each other before they act. What approximation method should you pull from the transcripts to solve this?
Oh, you would deploy a concept called correlated equilibrium via cheap talk.
Cheap talk. That sounds so unscientific.
I know, but it's a real term. Because computing the exact Nash equilibrium is impossible, you just allow the agents to engage in cheap talk, meaning non-binding communication, basically broadcasting, hey, I plan to go left on this turn.
But they can lie, right? It's non-binding.
They absolutely can lie. But because it's a general sum game where mutual benefit is actually possible, lying isn't always in their best interest.
Oh, because if they tell the truth, they might both get a higher reward.
Exactly. This cheap talk allows for a limited, highly efficient form of coordination. It serves as a really solid mathematical approximation of the perfect solution.
So you bypass the whole PPAD hard computing nightmare.
Yes, you bypass it by just letting the agents talk it out and reach a correlated equilibrium without needing complex side payments or incredibly deep cognitive modeling.
Let's run our final engineering scenario, and this brings us all the way back to the beginning, to single agents. Scenario 1.
Coming full circle.
You are programming a robot to physically navigate a massive warehouse. You do not have a predefined model of the warehouse physics or the exact reward structure. But you do have a highly accurate digital twin, a simulator that can run millions of transitions rapidly.
Okay, a simulator is a huge asset.
Right. So which of the three approaches to reinforcement learning discussed by the professor do you use? Policy search, model-based, or value function?
You would use the value function-based approach, specifically something like the Q learning we discussed.
Trace the logic for me. Why not the other two?
Well, policy search is just too indirect here. The raw simulator data doesn't explicitly tell you what the optimal action is in any given state, so blindly searching for a full policy is incredibly inefficient.
And model-based. Why not that?
Model-based requires you to build a perfect, explicit mathematical model of the transition matrix and all the rewards, and then use heavy planning algorithms to solve it. With a massive warehouse, the state space is too big. It's massive computational overhead.
So value functions are the sweet spot.
The professor literally calls it the Goldilocks balance. Value functions provide direct, actionable learning straight from the simulator's transitions.
By backing up those expected values, like we said earlier.
Exactly. Backing up the values, leaving that scent trail without the paralyzing overhead of heavy mathematical planning. It's just right.
Okay, let's take a deep breath. Because if you are listening to this and you tracked with us through those concepts, those mathematical edge cases, those scenarios, you just survived the ultimate conceptual stress test into reinforcement learning and game theory.
You really did. That was intense. And I think what this entire exercise proves is that those multiple choice practice quizzes barely scratch the surface of reality.
Not even close.
The real mathematical depth, the true understanding of why an algorithm converges, why a rigid strategy spirals into mutual destruction, and how to apply these abstract theories to noisy, real-world data.
Yeah.
It's all buried in the nuance of the conversation in those transcripts.
It is exactly the difference between memorizing the dictionary definition of a hammer and actually understanding the physics of how to build a house that won't collapse in a storm.
Exactly. Well said. And, if we connect this all back to the bigger picture,
Right.
there is a brief, almost throwaway mention at the end of the transcripts about a concept called mechanism design.
Oh, I saw that. Mechanism design is essentially the reverse engineering of game theory.
Right. It is the idea of using game theory to actively structure human society.
Wow.
The professor gives a very grounded real-world example using tax breaks on mortgage interests. The government wants to encourage homeownership rather than renting because homeownership theoretically stabilizes neighborhoods. So what do? They change the reward structure.
They give you a literal financial tax break.
Right. They are literally altering the environmental rewards to change the policy of the agents in the system.
Us. We are the agents.
They are the agents. So if a digital reinforcement learning algorithm can completely optimize and fundamentally alter its life policy purely based on the abstract rewards and transition probabilities we set, what does that say about human behavior?
Man.
Are we all just executing a highly complex, nonlinear value iteration based on the societal rewards designed around us? Are we just wandering around backing up our Q values, trying to maximize our utility?
That is a staggering thought. Are we playing Pavlov, or are we stuck in a tit-for-tat death spiral with our neighbors?
It really makes you wonder. Think about what your personal gamma discount factor is the next time you make a major life decision.
Oh, that's good.
Are you operating under an infinite horizon, planning for a future that extends beyond your own life? Or are you acting like the game is ending tomorrow and taking the short, risky path past the trap?
That is exactly why we do this show. We started today by saying the world of advanced machine learning isn't a clean X-ray. It is a landscape of murky waters.
Very murky.
But by diving this deep, by actively interrogating the logic, the math, and the underlying theory, we start to clearly see the shakes moving in those waters.
You really do.
We start to understand the physics of the algorithms that are, quite literally, shaping the architecture of our modern world. So keep questioning those algorithms. Keep looking for the missing areas. And most importantly, keep learning. Until next time.